Algebra 2, Section 11.4, Arithmetic Series. Start with a demonstration, a quick example of a couple of things. Finite sequence is a list of numbers, 6, 9, 12, 15, 18, whereas an infinite sequence could also be a list of numbers, but it uses the ... okay? So if you understand the word finite means that it ends, and infinite means that it doesn't end. This is finite because there are 5 terms. 6, 9, 12, 15, 18. This one is infinite because it's saying this continues. Now we understand both of these. We should right now understand what both of these things do. We've seen a lot of this ... where we're saying things can continue. Okay. Now the new word today is series. And in fact, what the next 2 sections are going to do, 11.4 and 11.5, is go in the same cadence as 11.2 and 11.3 did. 11.2 was arithmetic, 11.3 was geometric as it relates to sequence. Now 11.4 will be arithmetic series, 11.5 will be geometric series. The word series in math simply means to add them up, okay? And that's really demonstrated right here. So here you have a finite sequence, here you have the related series, a finite series that is the sum of those 5 numbers. 6 plus 9 plus 12 plus 15 plus 18 is the finite series. Whereas for an infinite sequence, its related series would be 3 plus 7 plus 11 plus 15 plus ... Now you might look at that and think, what good is that? How are you going to be able to add up those numbers? And you would be correct. We're not going to be able to add up those numbers. This just continues forever, 19, 23, and on and on. And you're never going to get a handle on what that number is. That's basically the concept of this being an infinite series, an infinite arithmetic series to be exact. Now, the reason we do that will come clear in section 11.5 because there is a way to get a sum for some infinite series when it comes to geometric series, but you'll have to stay tuned for the lesson on section 11.5 to learn about that. So just for completeness, we included this, but really where are we going to live today is going to be here with finite series. Okay, so an example to start. Use the finite sequence 5, 9, 13, 17, 21, 25, 29 and write the related series and then evaluate the series. Okay, now when they say write the related series, this is one of the easiest questions you'll ever be asked in Algebra 2. To write the related series is to simply do this. Show that you're adding those numbers up. This is what it means to write the related series. Just add the 7 numbers up. Now let me remind you that when they give us this sequence, again, remember that's a word from section 11.2. It's arithmetic and sequence was from 11.2. This is A1, this is A2, this is A3, A4, A5, A6, A7 would be the name of the number 29 in this finite sequence. It's the same thing here. Here's A1, here's A2, A3, A4, A5, A6. 29 is A7. So we're adding up A1 through A7, and that's an arithmetic series. Now, you can add these up if you want to. It comes out to 119. Comes out to 119. And I'm going to leave that example there. We'll come back to that in a second, and then I'm going to click back over to the notes to talk about the next thing. We'll come back and then verify the formula that's here in this next thing. It says the sum of a finite arithmetic series, A1 plus A2 plus A3 plus ... plus A sub n, is this formula. Okay, now that's an important formula that you ought to know. This is one that we do make students memorize when school's in session. And I'm going to explain it to you in just a second, but do first realize that the notation that I was just giving you back on that first example is expressed here. A1, A2, A3, et cetera, until we have all the numbers up through and including the last term, which is A sub n. Okay? Now, notice that n occurs 3 times in the formula, and A sub n here is the last term. Okay? So that's because, like, again, just take the last number, or the last example, had 7 terms. This here would be A sub 7. That means you're adding up 7 numbers, and you should put a 7 right here in the subscript notation. S sub 7. I'll do that in a second when we use this formula. The number 7 would also go here, 7 over 2. And then, as I have defined over here to the right, A sub 1 is the first term, A sub n is the last term. Now, side note, the use of A sub n has changed slightly from the way we were using it in the early part of the chapter. I realize this, I admit this, I don't know a better way to do it, but you must just realize that the way we were treating a sub n before is like to say it's the current term, whereas now we're saying it's always the last term, right? That's just a slight adjustment anyway, but it does now stand for the last term, whatever that term is, whether it's the third term, the 10th term, or the 5,000th term. It's the last one. So this is the formula. Let's go back to that example and just verify that it's true. Okay, so S sub n would be S sub 7, because we're adding up 7 numbers, is equal to n over 2, again n is 7, times a1, which is 5, plus a sub n, which is a sub 7, which is 29. Okay, and then just real quick on my calculator, and I can see what some things are going to simplify to. So 7 over 2 is 3.5, and 5 plus 29 is 34. So I just did 3.5 times 34, and it does in fact give you 119. Okay, now you might ask at this point, why do we even need a formula? It would probably have been just easier to just add up the numbers. That's probably true, but the longer the related series becomes, the more you're going to want to use the formula. Okay, so I wanted to use one that was reasonable because I wanted to verify that you do get the same sum. But if we're adding up 20 numbers or 100 numbers, the more numbers are in the sequence, the more you're going to want to use the formula. Okay, so we get 119. Let's try that again in the next example. Here you have a staircase, uses cement blocks arranged 4 across as shown below. Find the total number of blocks in the staircase. So if we just go 1, 2, 3, 4, 5 rows, that's 4 plus 8 plus 12 plus 16 plus 20. And again, you probably without too much effort could add those up and realize that that's going to be 60. Okay? And again, if I just made this staircase diagram much wider this way with more, taller segments, the more you're going to want to use the formula. And let me just prove it to you right now again once more. There are 5 rows, 1, 2, 3, 4, 5. There are 5 numbers then that I have listed. This is A1, this is A2, this is A3. S sub 5 is equal to 5 over 2 times 4 plus 20. 4 plus 20 is 24, times 5 over 2, which is basically 2.5, in fact, does give you 60. Okay. The next thing, and this I believe is brand new to Algebra 2 students. I believe you've never seen this symbol before. It's called summation notation. This symbol right here is capital sigma in the Greek alphabet, and it means the sum of. Okay, now I'm introducing it to you now. This is going to play a major part in the math that you do in the future. Okay, so this is a symbol that you ought to know. Let that sink in deep into your brain right now, that symbol means the sum of. Okay, now specifically the sum of what? Well, the number that's on the bottom here, usually we'll say n equals and then a number. That number that's on the bottom is the least value of n, whereas the number that's given on the top is the greatest value of n, letting n be integers. Okay, so n in this case is going to be 1, 2, and 3. And then what goes here, and you don't really need parentheses here, but our book, when it's more than one term, our book always puts it in parentheses. What's here is the explicit formula. Okay, now where did that term come from? Explicit formula came from 11.2 and 11.3, the sequences, right? So that's the explicit formula for a sequence. In this case, it's arithmetic, an arithmetic sequence, and we're looking for the sum. Okay, so what is this asking? You might look at this and just be confused. What this is asking is for us to be able to go 5 times 1 plus 1 plus 5 times 2 plus 1 plus 5 times 3 plus 1. 5 times 1 plus 1 plus 5 times 2 plus 1 plus 5 times 3 plus 1. It's saying do this for all of the integers in between and including these two numbers, the least and the greatest number. So I did 1, I did 3, and then every number in between, which was just, in this case, just 2. Okay, well, 5 times 1 plus 1 would be 6. 5 times 2 plus 1 would be 11. The next one would be 16. And that is an arithmetic series. That is an arithmetic series with 3 terms. The first term is 6, the last term is 16. They would add up to 33. And you've already seen me use the formula twice, so I don't really probably need to use it again, especially on just 3 numbers. But you could, okay? Now, and again, just by naming, this would be A1, this would be A2, this would be A3. We're adding up A1, A2, and A3. That's what this is trying to model. Use 1, do all the numbers in between, 1, 2, 3, 4, etc., up to, but in this case, the greatest number was just 3. Okay, back to another example. This here says use the summation notation to write the series 8, 16, 24, etc. for 50 terms. Okay, so they give you the information for the series and you have to write it using summation notation. So you should do this. Show that, capital sigma. If it's 50 terms, go n equals 1, and then on top should be 50. And then we need to come up with, just like we would have had to in section 11.2, we need to come up with the explicit formula for the one that gives us 8, 16, 24, etc. Okay? Now, what is that? Well, that's a sub n is equal to a1, which is 8, plus n minus 1 times d. What's the d? What's this going up by? 8s. And you should simplify this. We had a little bit of exposure to this in 11.2. You should simplify these into linear form by distributing the 8 and then simplifying. That would be 8 plus 8n minus 8. The 8 and the minus 8 would add up to 0, and you're left with just 8n. So what goes here, and again, you don't really need the parentheses. I'm just including them. But what goes there is 8n. All right, now listen. This is not my favorite type of example. We will do one more. I'm not crazy about it when the first term and the common difference end up being the same number, 8. Okay, so a lot of times this will be 4n plus 3, 3n minus 2, something that's in linear form that has a, let's just use the right terms, a slope and a y-intercept. Okay, here the y-intercept is just assumed to be 0. Okay, but that's the summation notation for that, 50 terms and 8n. And by the way, if you wanted to find that sum, that'd be the sum of 50 numbers, and it would be equal to 50 over 2 times the first term 8 plus a sub n. Let me just pause right now and let you think about that for a second. What would be the last term? Did you say 400? 50, when I plug 50 in, right? But to do this related series, 8, 16, 24, those numbers are coming when you plug in 1 and then 2 and then 3 for n, right? 8 times 1 is 8. 8 times 2 is 16. 8 times 3 is 24. Well, 8 times 50, the last term, 8 times 50 is 400. Okay? So then if you just then do on your calculator 50 over 2 times 8 plus 400, it's 10,200. That's what the sum actually would be. Now, they didn't ask for that here. You really only need to answer the questions they're asking for, but that is what the sum would be. And that's proof better than anything that the formula is worth something. Okay? You don't want to do 8 plus 16 plus 24 plus 32 plus et cetera, 50 times. All right, almost done. Let's try that again. Same directions. Use summation notation. This would look like this. N equals 1 to 9. That's what this means, right? It's 3, 8, 13, 18, et cetera, for a total of 9 terms. 1 to 9. And again, little side note here. 3 plus n minus 1 times d, where the d is 5. That would be 3 plus 5n minus 5, which would be 5n minus 2. This is 5n minus 2. That's what they would want. Okay, one more example then. It says use the series n equals 1 to 4 with the summation notation of negative 2n plus 3 to find the number of terms in the series, find the first and the last term, and then it says to evaluate the series. So that's actually a three-parter there. Okay, so this is basically the opposite. They're not asking to write the series. Now they're giving you the series and they're asking you a bunch of information about it. Find the number of terms in the series. Now, it's not as simple as subtracting. Too many people over the years I've seen go 4 minus 1, it's 3. No. It's 1. I'm counting on my fingers. 1, 2, 3, 4. That's 4 terms. The number of terms in the series is 4. So if you're going to subtract, you need to add 1 to your difference. 1 to 4 is actually 4 terms. And then it says find the first term and the last term. That's easy enough. All you need to do there is plug 1 in for n and then plug 4 in for n, and you'll have the first and last terms. Negative 2 times 1 is negative 2, plus 3 would be positive 1. The first term would be 1. Negative 2 times 4 would be negative 8, plus 3 would be negative 5. The last term would be negative 5. Okay, so they wanted the number of terms 4, the first term would be 1, and the last term would be negative 5. And why do they ask all that information? So that you can plug it into the sum formula. The last question, I'll just leave it on this page. The last question says evaluate the series. So that's the sum of 4 numbers, which is equal to 4 over 2 times 1 plus negative 5. You see how all these numbers played in? This 4 is this 4, and it's also this 4. And in fact, it is the 4 that is in a sub 4. This 1 obviously went here. This negative 5 went right here. And what does that give us? Is it negative 8? 1 plus negative 5 is negative 4 times 2 would be negative 8. And that is the sum of those 4 numbers. That's the sum of the numbers that you would get if you plugged in 1 and 2 and 3 and 4 in for n and took those 4 numbers as outputs and added them together. And they did that, and they got negative 8 also. Okay, so finally, just to kind of wrap it up there, similar questions here. The number of terms, we'll take this one across, then we'll do the last one, which is a little bit trickier. The number of terms from 1 to 10 would be 10 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The first term would be what you get when you plug in 1. 1 minus 3 is negative 2. The last term would be what you get when you plug in 10. 10 minus 3 is 7. And evaluate would be 10 over 2 times negative 2 plus 7. 10 over 2 is 5. This is also 5. That comes out to 25. Okay? By the way, on a homework assignment that's like this, I think it's probably a good way to organize your homework if there's several problems that are like this, to just do as I did with headings across. As you look at their answers, they might just like separate them by a comma or whatever, but it's really nice to put a heading there, and then you'll have to do it one time. It should be pretty efficient. Okay, lastly, and pay attention to this last one. Don't check out. I know the video's gone a little long today, but this is the last one. You need to hear this. N equals 2 to 5. This does not have to be 1 on the bottom. It often is. It does not have to be. This does not mean that there is no first term. It just means that we're not including it in the sum. Okay? We're starting at, remember this symbol means sum. So we're just, yes, there are terms that are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the first, the second, the third, the fourth, all the way. We're just not including the first one in the series. We're adding up the second, third, fourth, and fifth numbers. So with that, from 2 to 5 would be 2, 3, 4, 5. That'd be 4 terms. The first term would be what you get when you plug in 2. 2 squared is 4. The last term would be what you get when you plug in 5. That's 25. Now, caution, not only is this problem a little bit different because it started at a different number than 1, it's also not linear, so it's not arithmetic. We can still use summation notation even though it's not arithmetic. Most of what you do in the homework today will be arithmetic, but not all of it. Okay, so this is quadratic. That's something different. It's not linear. Anyway, we can still add up those numbers. You can't use the formula either because it's not arithmetic. But we could simply add up those numbers, because what you're really adding up is 2 squared plus 3 squared plus 4 squared plus 5 squared. And that sum would be, I'm adding them up in my head, 54, just by adding them up. Okay? All right, thanks for bearing with me there on a kind of a long video. Have a good day.